today we will perform very simple thermal heat transfer analysis, and as you saw, the main object of today's example will be the manifold exhaust. So this example will be performed in analyst mode of midas NFX. So I'm just checking if the mode has been checked correctly. So let's start doing the example, and I will try to explain to you the basic steps to accomplish this tutorial. So first step is selection, the proper model type and selection of the unit system. So today we will perform a 3D heat transfer simulation, and we will use SI system units. So to change, for example, the unit of length, you have to click on this menu and you can change, for example, to meters. So at this moment I have SI units. So at this moment I'm clicking on OK, and I'm going to this geometry tab, and I will import the exhaust geometry. So basically in midas NFX you can import many types of CAD formats. If you take a look on this menu what I'm showing at this moment, you can see that midas NFX supports most popular CAD formats like CATIA, SolidWorks, Unigraphics, Inventor, Solid Edge, and some of the standard formats are also supported, like for example Parasolid, ACES, STEP, and IGES. So at this moment I will use the exhaust geometry which has been prepared in external CAD system. Okay, I have to select, and let's see the geometry. Okay, so now we see this, and let's hide the all guiders. So before we start, I think it will be good when I say at least one sentence to explain what the manifold exhaust is. So this is a part of the engine, and it's used to collect the exhaust gases from the multiple cylinders into one pipe. So here we go. Here we see this. So we have a lot of holes from the pipes, and all they are used to collect the gases, and the gas is flowing out from this side of the geometry. So let's start the example, and I will go to set up the material properties. So this is the basically the first step. So let's click on Edit, and for this simulation, the only thing we have to. Okay, so I received that some information that. My question is, do you hear us?
I think we have some problem with the sound. Is everything hearing what you say, or can you just leave some message? We'd like to.
Okay.
Okay. So okay.
Okay. So let's back to midas NFX. So please tell us if something is wrong with the streaming. Okay. So basically we starting from the thermal material properties, and for this simulation let's specify coefficients like conductivity coefficient. So I will start from this, and basically we can change this to a little bit slower value, but I'm just doing this in case that you will define your material manually. So you have to enter this value, you have to define the specific heat, and we can work with this value, and that's all for this simulation only. So in terms of structural parameters, I will specify, or actually I will add some parameter which is called reference temperature, because my intent is also to show you the thermal stress analysis, and this is why we need these parameters as well. So I will specify this reference temperature to 65 degrees of Celsius, and this will be basically my unit. So the rest of the parameters like elastic modulus, Poisson's ratio, and mass density are fine, so I'm just clicking on OK. So the next step is to define the property. So I'm always doing these steps in this sequence. So So I think it's a quite good school. Okay, so let's add 3D property, and let's simply click on OK to specify the property. So we have this. Okay, so the next step is application of the thermal boundary conditions. And this is quite interesting thing, because as we see, the model is, there is a one part, but at least it's a little bit complex, because there are many curved surfaces, and our task is to apply some boundary conditions like convection on, or heat flux on the inner part or inner surfaces of this geometry. So how to do this efficiently? So with help comes our selection toolbar. This is very useful tool, and I will show you how to use this efficiently. So our task is to select all of these inner faces from the pipes. So basically, the selection toolbar consists of a few parts. So this is the first part, which describes the selection mode. So you can select entities or you can deselect entities. So okay, at this moment I will leave this option like that. The second column describes the selection method. This part is called selection filter. So we can select edges, faces, points. So this is our filter. And the rest of the parameters are very useful in terms of the additional parameters which will be helpful for the selection. So basically, let's apply the flux on the inner faces. So I'm clicking on the heat flux. So as you see, the dialog box appeared, and from the object I'm changing the type, and I'm selecting the face. So I will apply this condition on the geometry faces. So how to do this efficiently? Because at this moment, the only thing what we can do, we can start to select them manually. And we have a problem because it's very difficult to select the inner faces. But how to do this efficiently and very easily? So there is one option which is called select neighboring edges or surfaces with feature angle. So we're supposed to start from this option and set up the feature angle. So we can set up for 20 degrees, for example, or let's say for 10. But I think the 20 is quite good option, and you're supposed to exercise this option by yourself. And now I will show you how to select this, all of those faces. So all you have to do is simply to select one face from first pipe, let's say, second face, third one, and fourth one, and please click on this option, and you will see what happened. All of the faces has been selected automatically. And how to preview this? If you go to this option, to this view toolbar, I will change the displaying into the lines, and now you are seeing that all of the internal faces has been displayed. So this is a very big advantage of our selection toolbar, especially for the thermal simulations where the shapes are really, really complex. Okay, so okay.
Very nice. I didn't know we could do that, Piotr.
Now you know. Okay, so let's apply the value for heat flux. So it will be like 40,000. And let's click on OK. So as you see, the whole job has been done. So we are saving a lot of time. So let's change the displaying to the previous state. Let's back to the previous state, and let's click on the shading and line. And now I'm going to the slot and boundary condition, and I will hide the displaying of the heat flux because I want to work on the, let's say, lighter view. Okay, so now the second step is to assign the convection factor. So as Cyprian said previously in the PPT part, we have three ways, three methods to work with the thermal loadings. The heat transfer can be applied via conduction, convection, and radiation. So at this moment we will work more or less with the convection. So I'm doing the same. From the object I'm selecting the face, and this time I will select all of external faces. So basically I will use the same command because it's very useful, as you saw. So once again I'm selecting some faces, and I'm using this button to select neighboring faces, and as you see, all job is done. At this moment I'm selecting only the faces which are quite far from the feature angle. And what can we say? This option will be also very useful in the structural analysis, especially if you want to fix the structural part on the bolted holes. So we are always spending a lot of time to select all of these inner faces. Now we can simply select few of them and use this feature selection option, and every kind of hole will be fixed, let's say, in terms of the structural. But let's back to the thermal again. So I think we can leave this selection like that, and let's apply the film coefficient, and this time it will be like 110, and as you remember, this will describe more or less forced conditions because the value is quite high. So let's click on OK. Okay, we have it. And what can we do at this moment? Now we can go to the mesh and perform the mesh generation on our part. So now I'm clicking on 3D, and we will use the automatic mesher. Basically, NFX has been equipped with tetra mesher and a hybrid mesher. And during this presentation, I will use the tetrahedral generation option. Now I'm unchecking the higher order elements, so we will work with the linear elements only because they are valid for the thermal purposes. Okay, so we have it, and let's change the element size to 0.1 meter, which means 10 millimeters. Okay, let's specify the name. And let's click on OK. Oh, I forgot to select the part, and at this moment everything should be fine. So let's wait a few seconds for the meshing. As the news, we can share with you one thing, that in the next release of Midas NFX, the new type of mesher will be developed. We will get the new fully hexahedral automatic mesher, but we will of course inform you via emails and via our marketing campaign. So as you see, we have the model has been divided into elements, and basically we can say it's ready for the analysis. So now I'm going to analysis and results tab from my model tree. I'm going to the other, and I'm selecting the nonlinear steady heat transfer. So we start from this analysis. This is the basic basic heat transfer analysis inside Midas NFX. So at this moment I want to perform the linear steady state transfer analysis, and to do that we can use this option and simply change the number increments into the 1, and we will get exactly the same result. The other parameter that we should define is the initial temperature, and the initial temperature will be set up to 65 degrees of Celsius, and that's all. So now I'm clicking on OK, and let's start the calculation. So the model is not so heavy in terms of the size and number of the nodes, so the analysis will take only a few seconds, like almost 3 seconds, for example. And let's go back.
It's quite fast.
It's quite fast, and let's display the results. So we see this is the result of our very simple thermal analysis according to the first example.